Hello class, this is Mr. Blevins. We're going to go over the second discussion, which was the other fundamental theorem of calculus. So what we're used to seeing, or what I always think of when I think fundamental theorem of calculus, is I think if I want to find the area under this curve, then I find the antiderivative and I plug in b into the antiderivative. I plug in 1 into the antiderivative and subtract. And that is the fundamental theorem of calculus, one part of it, but this other part deals with the rate that this area is accumulating. And so what I mean by that is, as I move off of the starting point of an area, so I'm moving away from 1 towards the right, and I'm starting to accumulate area. Well, as I accumulate area, how much area I accumulate as I move to the right can be given by a function. I can come up with a function, and the function is basically what is the area, like this gray area, at a particular value of x. So right now our x is right here between 3 and 4 at 3.5. And as it goes up to 3.6 and 3.8 and 3.9 and 5 and on and on and on, there is a function that will output this number right here that will tell me that when x is 6.15, this is the output of that function, the area that we've accumulated starting at some starting point 1 in this case. Alright, so what this lab does is it has you derive that area formula. Not derive it, but just examine properties of it. What would this function look like? So as I gain area, alright, I'm gaining area, so it's always getting bigger and bigger and bigger, but it slows down in its growth because we're obtaining less and less and less area. So that's what this lab was about, was what would this function look like that described the compounding of area for this particular function f. Alright, so as you went through here, you were supposed to come up with what is the area between 1, and this should have said b here, but what's the area between these two? So if I go to 5, so if I take this thing to 5 right here, alright, I get 1.6094. 1.6094 would go into this box. 1.6094. Alright, and then what goes in this box is the difference in that, is what it explains in here. That I take a calculator and I just subtract the difference between this and this. So this was just the 1.0986 minus 0. And now I'm going to do 1.6094 minus 1.0986, and that's what's going to go in the change. So 0.5078. Alright, and then I go back and do it again for 7. So I go back to here, I extend this all the way to 7, I get 1.9459. 1.9459. And then I can just subtract that, and I'll just change the sign here because I'm doing this one minus this one rather than the other way around. So it's a positive 0.3395. And the thing you're supposed to see here is the change in area that's accumulated as I move up the same distance is slowing down. So we are gaining more area, so it's still positive. You know, the rate that the rate that the curve is changing is positive, but the change in rate, the change in area accumulated is negative. Change in the rate of accumulation is negative. So we're always gaining more because it's a positive area that we're gaining. So we're adding more area all the time. But the rate at which we add area is decreasing. And that's what this is telling us. Alright, so the questions that you're asking, question 1, how is the rate of area accumulation changing? It's going downhill. So everybody's got their formulas right, but how are these areas changing? The change in area is decreasing. The rate of area accumulating is decreasing. Good. The responses I'm seeing is this rate. It's important that we see the rate is decreasing. So that's the kind of things that I wanted to see on here. All right, the rate at which the increase is decreasing. Very good. All right, so that was the big first question. Now the second question, where is this area accumulated equal to 0? Well, the area is going to be equal to 0 when a is equal to 1. All right, when we haven't accumulated any area yet. So when x is equal to 1 in our new function, a will be equal to 0. Or sorry, the area that our function will be equal to 0. So this should say the function g of x is only equal to 0 when x is equal to 1, not f of x. All right, so same thing here. X is equal to 1, that's good. All right, now where would g of x be positive? Well, remember, g of x is how the area that's accumulating. So it's going to be positive everywhere beyond x equal to 1. So everywhere beyond x equal to 1, because we don't ever go below the x-axis. That's great. We're never decreasing with our area, so we're always gaining area. Okay, we're always gaining area. Where would the derivative of g of x be positive? So g of x, again, is our function that's talking about how we're gaining area here. So we're always going to be gaining area. So g of x is the amount of area that we've accumulated, and we're always gaining area, so the derivative will always be positive for x greater than 0. All right, how do we know the derivative is always positive? We're never losing area. We're never dipping down below the x-axis. The graph of this thing is never going downhill as we move left to right. So we're always gaining area, so our derivative is always positive. All right, and then the question says, is the derivative ever negative? No, it's never negative because, again, we're always increasing our area. All right, what about the second derivative? Is it ever negative? Yes, the second derivative is always negative because, again, with our graph, if you look at this thing, as we make our way left or right, we're always gaining area, but the rate at which we gain area is going downhill. That's what the table was showing us. We're gaining area still. We're always gaining, so it's always positive, but we're gaining it at a slower and slower and slower rate. So the second derivative will always be negative for all of these. All right, always negative. And good responses. Some initially mentioned the fundamental theorem of calculus, which is what we're trying to derive here. So if you mentioned that, I sent you an email to change that and just look at the graph and talk about derivatives as rate of change rather than the name of the activity. All right, now in this third slide, I revealed the blue curve. So we get to see the blue curve for the first time. And we see that this blue curve, the y-coordinate, the height of the blue curve is giving us the accumulated area. All right, so this is accumulated area. This is the height of the blue curve. And so we see this thing is the blue curve is equal to 0. We haven't accumulated any area when x is equal to 1. All right, so we're starting at 1. When b is 1, meaning the starting and stopping point of our integral is the same number, we don't have any area. We don't have any width yet. So this is equal to 0 when x is equal to 1. And then as we go to the right, it's increasing. And as we see, it's always positive. It's always above the x-axis. And it is the slope of this, the derivative, is positive, but it's becoming less positive as we go on. All right, meaning that the derivative is becoming less positive. It starts off as steep as it's going to be, and it's becoming less and less and less steep. The derivative, the slope of the tangent line is at these given points. So again, I just plotted this on here, this dashed line. This is the derivative. And we can see again, that line is as steep as it's going to be, and as we make our way to the right, we can see it's becoming less and less and less and less and less steep as we make our way to the right. So the derivative is positive, but that shows us again that the second derivative is negative because the second derivative is the change in the first derivative, the change in the slopes. And since the slopes are decreasing, that second derivative would be negative everywhere. We can also see the second derivative is negative because this thing is concave down everywhere. All right, so those answers were here as well on the questions about the first and second derivative. We can see those with the responses. Most of you guys got those right as well. All right, and then finally I reveal what these functions are so we can see the mathematical relationship between them. So the red function, our original function, was 1 over x. Okay, 1 over x has that part over here to the left, but we're only concerned from 1 to infinity, so that's why I don't show that other part of it. But we are accumulating area underneath the graph of 1 over x from 1 to b. And we're seeing that the natural log function is what's giving us that area. Now, I asked you the mathematical relationship between these. Well, the derivative of 1 over x, the derivative of natural log of x is 1 over x. Natural log is our area accumulation function. Okay? We're accumulating area under 1 over x. That's what this is. So we're accumulating area under here. That area accumulation is given by the natural log. So remember, antiderivatives give us the area accumulation, and then the natural log is the antiderivative of this, but the derivative of this, of natural log, the area accumulation function, is back to the 1 over x. And that's what the fundamental theorem of calculus tells us. It tells us that if we are accumulating area under a function from starting point, a is just some number, to some variable, some value that's allowed to change, then the area that's accumulated from this point to that point here is the antiderivative. F, capital F, lowercase f, that's the same antiderivative notation we got in Calculus 1. And the derivative of this, how this is changing, is given by the function's height itself. So how is the area underneath the curve of 1 over x, how is it changing at the exact moment when b is equal to 3.6? How is this area accumulating changing? Well, it would be f of 3.6, or f of b in this case, 2.77. That would be the slope of this thing. If I did g prime at b, I'm going to do 3.6 again, we get to 2.77. The rate of change in accumulation of area is equal to the height of the function that the area is accumulating under. And that's exactly what the fundamental theorem of calculus is telling us. The big interpretation of what this is saying is the rate of change in area the rate of change, how this area accumulation function is changing, is literally the function that we're talking about, the function that we're accumulating area under at the point that we have stopped our area accumulation for a specific starting point. Okay, now that was the big thing, for a specific starting point. There is a value where this is true for a specific, because again we're talking antiderivative. So our function could have a plus c that goes away when we do the derivative. So we may have to make an adjustment. So for the last part, for the bonus part that you guys had to do, you had to come up with something where as I moved this, the height here was equal to the area accumulated. And sine and cosine is perfect. Again, they have that derivative and antiderivative relationship. All right, but for some of you guys, it wasn't exactly the same. And what I mean by that is, for this one right here, if you look, our area that we've accumulated according to this is 25.185. And this is 20.185. So it's off by 5. So that means that this number down here is not the right number that it should be, or this number here, our value whose derivative we have here, is not exactly correct. So notice this, if I do minus 5 here, I get this function. Now the height is 20.185, 20.185, they match. Well, what's the derivative of this? Well, it's still going to be 4 over x plus 5. It's just because of the constant there that everything's adjusted. Okay, now the other thing you could have done is this number, this lower number here, could also be adjusted. But that would have been a much tougher thing to do to come up with what the actual lower number should be here for this to work out than it would be here when I see that they're exactly 5 off and adjust it with the -5. So notice it still has the property, that the derivative of g is f. It's just that we had that constant to get the areas to match up. All right, I hope that you found that informative. The fundamental theorem of calculus has 2 parts, and a lot of people forget this part of it that deals with the rate of change of the area accumulating underneath the graph of a curve.